Hello! In this week's experiment, we are going to talk about chemical kinetics, initial rates of reaction. And we will talk about what is chemical kinetics, what factors influence reaction rate, how do we even define the term reaction rate, and then we will go into the specifics of our experiment. So, in general terms, chemical kinetics deal with the speed of a chemical reaction, which would be the rate of reaction, and the steps involved in the mechanism of a chemical reaction. So that would be the umbrella term, chemical kinetics. And so what are the common factors that influence the reaction rate? We have three most common factors, which is the concentration of reagents. Here, reagents could be the reactants or the catalyst or intermediates or products. And also the temperature in which the reaction takes place at, and also the catalyst. So the rate of reaction is proportional to the concentration of the reagents. This is just to say when you have a higher concentration of your reagents, then the rate of your reaction will be higher. And with the temperature, there are reactions where with increasing temperature, then the rate of reaction goes up. And we all know that catalysts are substances that speed up the rate of a reaction. And we will see how these three factors affect the rate of the reaction in which we will conduct this in this week's experiment. Alright, we just established that the concentration of reagents determines the rate of a reaction. And so why do we use the term initial rates of a reaction specifically for the experiment in this week? Well, we know that we know that over time the concentration of our reactants are going to go down because we are using up the reactants to create the products, right? And if that's the case, then we expect that the rate of reaction will go down following the decrease in the concentration of our reactants. And because we only want to capture the initial rate of that reaction, we are going to conduct the experiment during and observe the rate of reaction during the first few minutes of the reaction, where we assume that the concentration of reactants do not decrease significantly. So that's why you hear the term the initial rate of a reaction. So this is the way to express the rate law of any reaction, where if you have reactants A combining with reactant B to form product C, the rate expression for that reaction would be given by this equation here. Rate is equals to K, is the rate constant for the reaction, and then your concentrations, or the concentration of your species, which could be the reactants, the products, intermediate, anything that affect the rate of a reaction is included in the rate law expression. And then the N, the M, and P are integers. They are not stoichiometric numbers as you would usually see in an equilibrium expressions, but these values have to be experimentally determined, and we are going to talk about specifically how to experimentally determine these numbers. Just going to the specifics of this experiment, we are going to look at hydrogen peroxide and its decomposition to produce oxygen gas. So hydrogen peroxide decomposes, and we have water and oxygen gas as our products. And this makes it possible for us to monitor the rate by looking at the volume of oxygen gas being produced per unit time. So we are going to have our three factors in play here because, one, we are going to use the iodide, which is a non-catalyst for this reaction, as our catalyst. We are also going to vary the concentration of the potassium iodide and the hydrogen peroxide. And finally, we will carry the experiment under two set of conditions. One at room temperature, which is at 25 degrees Celsius about, and the other one would be at a higher temperature, about 45 degrees Celsius. And so having these three factors in play, we are going to see how does the volume of oxygen production change when these three factors are at play. So again, we are interested in how to determine the values N and M, because we said we cannot just use the stoichiometric numbers for that. We have to experimentally determine these values. So the first thing that we have to do once we have our expressions and we have our varied conditions. So here we have, for example, A. You can take A as hydrogen peroxide and B as your potassium iodide. And the numbers associated with them would be the N for the hydrogen peroxide and the M for the potassium iodide. So we have two reactants and then we have different concentrations or different conditions for this. But let's look at specifically the concentration. So let's assume that this is your run 1, this is your run 2, and that's your run 3. So if you want to determine the values of the N and M, you have to look at what is the variation between the concentration of my reactants and how does that affect the rate of my reaction. So let's compare runs 1 and 2. In run 1, the concentration of A is 0.5 molar and the concentration of B is 0.5 molar. In run 2 though, we have the concentration of A remaining at 0.5 molar, so it's the same, it's constant. But the concentration of species B is now 0.1, which is a double. So that means that if I double the concentration of reactant B, look at what happens to the rate of my reaction. It's going from 10 to 20, which is a double, right? Okay, so let's hold it there. Now compare runs 2 and 3 for you to be able to determine how the rate of a reaction is with respect to the specific species. One, you have to consider the conditions where where the concentration of one of the species is constant, varying the other one, so that we can say, well, the rate of reaction here is due to the concentration of B. Okay, so comparing runs 2 and 3, as we said, keep the concentration of one thing constant. So here we have B is 0.1 and 0.1. But the concentration of A is going from 0.5 molar to 0.1 molar. So we double the concentration of A. And it resulted to a quadruple increase in the reaction, the rate of reaction. It's going from 20 to 80, which is like 4 times more. Okay, so how do we interpret these numbers? So let's go ahead and look at this other slide and see. So we said here when we double the concentration of B and keeping A constant, the rate of reaction doubles. So when you have a scenario where when you double the concentration of a species and the rate doubles, that is defined as first order with respect to the species that is being varied. That's that concentration is being varied. So we have here first order with respect to B, and in that case our value, let's go back to the previous slide if we can. Okay, I don't think so, but anyway, so with respect to B, then the value N would be 1. Remember we had, for example, N and M here. So your N will be 1. We have established that. And when it comes to A, we said when we double the concentration of A, the reaction quadruples. So that scenario is termed as second order, and it would be second order with respect to the species in which we are varying the concentration, in this case A. And so we have our M is 2. Okay, so what would be the scenario where we have no change in the rate of reaction when we double the concentration of A or B? So just again, we could take the 0.5 to 0.1, and what if in case instead our reaction rate, instead of going to 20, it just remained at 10? In this case, our rate of reaction would be no change, right? So when you double the concentration of your species, but the rate remains the same, then you have a zero order. Well, now just computing your overall rate law expression. To determine the overall rate law, you just add the numbers here. You have 1 with respect to B and 2 with respect to A. And you're just going to say 1 plus 2 would be 3, sorry. And that would be a third order overall. I hope that's clear. Okay, let's go to the next. So specifically applying this to our run, so we have the potassium iodide. This is the stock concentration that you're given, and then we also have the hydrogen peroxide here. You will notice that in these columns you have volumes. This is not concentrations, and therefore you have to compute your concentrations using the M1 V1 M2 V2 formula. So let's take, for example, in run 4 here, your M1 is 0.09 molar. Okay, I don't know if I can write really well here, but and then your V1 in run 4 specifically, you took 20 ml of 0.09. I'm sorry about the writing, but I'm just trying to show you how you will compute your M2. So we are interested in finding the M2, but always you will notice that your total volumes are going to add up to 30 milliliters. Okay, so that's your V2. And what you can do is just cancel out all of this and determine the value of your M2 here, which I assume to be 0.06 molar. Okay, so anyway, I just did this for Ki run 4. That means you have to do it for Ki runs 1, 2, 3, 4, 5, 6, and then do the same thing for your hydrogen peroxide to determine the concentrations. And now again, go back to the slide, the previous slide. It is very important for you to use that slide because you will be comparing the concentrations. So if the concentration, assuming that the concentration for the 10 ml was, for example, 0.03, then going from 0.03 to 0.06 in run 4 is a double. And you can also see that here, for example, let's assume that if this volume, if the concentration here was 0.1, then the concentration here is also 0.1. We know that hydrogen peroxide is constant. So then it makes it easy for you to compare how much volume of oxygen is collected in run 1 and how much volume of oxygen, well, the rate of production of oxygen in run 4. Then that would be because here hydrogen peroxide was the same, but the concentration of potassium iodide was doubled. So just look at the numbers that you get here, and that should give you how to determine the rate of reaction for that specific order. So you will be expected to generate graphs for all the 6 runs that you have. You could choose to do all the 6 lines in one graph if you want, but if you prefer to have the 6 different graphs from the different runs, that's okay. But you will realize that your data will look something like, at the beginning you have a linear relationship, but then it plateaus over time, because we know that the rate of reaction is really high in the beginning and then it kind of levels off. So you'll be interested in the rate, like at the first few minutes, where you see the linear line, where you see the linear fit here that you can use. So finding the graph, finding the slope of this here would help you define the rate of reaction for your specific run, and that should help you carry out the other calculations to determine the orders with respect to hydrogen peroxide and potassium iodide. So hopefully this was helpful, and you should be able to do the questions in your report sheet for this experiment. And good luck.